Hello, Astro people. So, now that we have defined the spherical triangle as the triangle formed by the intersection of three arcs of great circle, let's study more of their properties and see how they are useful in the study of spherical astronomy. One important property of spherical triangles is the fact that the sum of the angles is bigger than 180 degrees. That's different from plane triangles where the sum is always 180 degrees. You see here a plane triangle, the sum of the angles is 180 degrees. You see here a spherical triangle drawn on the surface of the Earth. You're forming this triangle here with two arcs of meridian plus an arc on the equator. The angle between the equator and the meridian is always 90 degrees. So you have here two angles being 90 degrees. And the other angle here is randomly at 50 degrees. But you can imagine a spherical triangle where the three angles are 90 degrees. Again, you form this triangle in here with two arcs of meridian and one arc on the equator. The angle between the equator and the meridian is 90 degrees, and you can pick two meridians that are 90 degrees apart. In this case, the three angles are having 90 degrees. So the sum of the angles is 270 degrees. An important definition in spherical trigonometry is the fact that for a sphere of unit radius, the arc of great circle connecting 2 points on the surface of the sphere is equal to the angle in radians subtended at the center of the sphere. You see it here on this figure. You have the angle here, AOB. A and B are points on the surface of the sphere, and O is the center of the sphere. The angle AOB is equal to the angular size of the great circle arc C. This comes directly from the definition of length on a circle. The length of the path C is the radius of the sphere R times psi, where psi is the angle AOB here in the figure. If you have the radius being equal to 1, then phi and c have the same units, and c is equal to phi. So this is how you can describe the spherical angle in terms of a plane angle. You have the arc PA, you draw the tangent PA prime, and you have the arc PB, you draw the tangent PB prime. The spherical angle that is defined by the intersection between these planes is the same as the plane angle defined by these tangents. Let's pass into spherical trigonometry and study more of these triangles. The first thing that we're going to study is the fundamental law of cosines. First, a note on notation. Usually we define the sides of the spherical triangle as lowercase letters and the angles as uppercase letters. The fundamental law of cosines relates sides and angles of a spherical triangle. It states that cosine of C meaning one of the sides, is equal to the cosine of B and cosine of A times sine of A sine B times cosine of big C. So let's see how we can prove this assertion. We can consider the spherical triangle as in the figure and let U hat, V hat, and W hat be unit vectors from the center of the sphere to the vertices of the triangle. Now, without flaws of generality, we can align U hat with the z-axis and make V hat lie on the xz plane. Now, in spherical coordinates, where a point is given by its coordinates radius, meridional angle theta, and azimuthal angle phi, the angle theta is measured from the pole. Therefore, the vector V hat in spherical coordinates is given by 1, a, and 0. 1 because it is a sphere of unit radius, a because that's this side going from the pole to the vector v, and 0 because we, by definition, made it coincide with xz plane. Now, for the vector w hat, we have that theta is equal to b, and its azimuthal angle is equal to this opening, the angle between the sides a and b, which, by definition, is equal to the angle c. Therefore, w hat in spherical coordinates is 1b and big C. Now let's convert this to Cartesian coordinates. For v hat, r is equal to 1, theta is equal to a, and phi is equal to 0. Therefore, x is equal to sine a. Y is equal to 0 because phi is 0. As for z, we have theta being equal to a, and r is equal to 1, so it's equal to cosine a. So we found here what v hat is in Cartesian coordinates is equal to sine a, 0, and cosine a. Let's play the same game for w hat. For w hat, you have r equal to 1, theta is equal to b, and phi is equal to c, so this becomes sine b and cosine c. Y is equal to sine of b and sine of c, and z is equal to the cosine of b. So you write this in Cartesian coordinates. Now, because little c is an arc of great circle and the sphere has unit radius, little c is the angle between v hat and w hat. You can see this by noticing that these two vectors meet at the center of the sphere, and this angle here at the center of the sphere is the same as the side c. That is, little c is the same as the angle BOA. So if you take the dot product between v hat and w hat, this must be equal to the modulus of v times the modulus of w times the cosine between them, which is little c. Now, because v hat and w hat are unit vectors, the modulus of v hat and w hat are by definition unit. So this reduces to cosine of little c is equal to the dot product between v hat and w hat. And the dot product between v hat and w hat is, given the definition in Cartesian coordinates, sine a, 0, cosine a, dotted with sine b, cosine of big C, sine b, sine big C, cosine b. Now it's equal to sine a, sine b, cosine c, plus 0, so we don't need the middle term, plus cosine a, cosine b. So if you equate now, call this 1 and call this 2, and then you have that cosine c is equal to cosine a, cosine b, plus sine a, sine b, cosine big C, which is exactly what you wanted to prove. So the theorem QED.